Hi everyone, in this CSE 373 review video, we're going to be going over Dijkstra's algorithm. So what does Dijkstra's algorithm do? Basically, given a weighted graph, the algorithm will find the shortest path tree for that weighted graph. And the shortest path tree is made up of all the shortest paths between some starting node and all other nodes. So if you look at the diagram on the bottom, we have some graph, and after running Dijkstra's, we will have this tree with reduced amount of edges where from our source node S, we can get to any other node and it's guaranteed to be the shortest path. If we want to find the shortest path between a starting node and a target node, for example, S to C, we can just go to C and then trace back the edges to S and we will find our shortest path. And now there are other ways to implement Dijkstra's where maybe you have a source node and a target node and you want to stop when you get to that target node. That is one way to do it. We're not doing it that way. We're actually going to be making these shortest path trees and then using traceback to find individual paths. So Dijkstra's is actually very similar to BFS. So if you're having trouble understanding some of the concepts with the Dijkstra's algorithm, definitely feel free to go back and review some of those BFS concepts that we taught you. One of these main differences between BFS and Dijkstra's is that Dijkstra's uses a priority queue instead of a regular queue to order traversal through the graph. And this priority queue prioritizes nodes with the smallest estimated distance from the starting node. So the next node in our priority queue will be the node that we think will be closest to the starting node that we haven't gone through yet. And Dijkstra's runs in theta of E log V plus V log V time instead of E plus V like BFS because we need this extra log factor to help maintain our priority queue. So here's the code that we want you to use as your kind of starting point when implementing Dijkstra's. It may seem daunting, but we're going to go through it like step by step. So first we have this initialization portion where we create two maps. One maps each vertex to its predecessor edge, and one maps each vertex to its distance from the start. And we're going to be updating this in our iterative portion of Dijkstra's. We also create this priority queue that we're going to use to order our traversal through the graph. And then to actually start manipulating, we initialize all the distances in our dist2v map to infinity. And this is so whenever we come across a new node, the path that we've taken to get there will always be less than infinity. You'll see this more when we go through the algorithm. Then to end our initialization portion, we add the start node with distance 0 to our priority queue, and then we put the start node in our dist2v map, again with distance 0. Next, we have our iterative portion of Dijkstra's. So let's just go through it line by line. First, we're saying while we still have some nodes in our priority queue, we're going to execute this. So while we still have nodes to traverse, we're going to execute the majority of the Dijkstra algorithm. So first, we remove the element that's next on our priority queue. So we remove min, and that's the node that we're going to be doing manipulations on in this main loop. So then for every edge in that from going out from that node, we look at the node that that edge is going to, and we first check what the currently stored distance is. For the first time, it'll be infinity. And then we calculate what the new distance would be by adding up the distance to the node we're at plus the weight of the edge going to the node at the end of the edge. And then if this new distance is less than this old distance, we're going to update our maps and put the node with the edge for the predecessor map and put the node with a new distance for the distance to V map. And then we're going to check if our priority queue contains this node. And if it does, we're going to update the priority to our new distance. And if it doesn't, we're going to add it to the priority queue to explore later. If that was confusing or too fast, don't worry, we're going to be going through this line by line very shortly.